Last class we discussed about discrete charges and the field due to them. That was the equation, that is we were talking, that is we had some charges, we can call it as some point charges, or they are distributed in the space discretely. You can count them 1, 2, 3. So, here you have a charge, here you have a charge, here you have a charge. But in actual practice the charges are not distributed like this. They are actually distributed over some space, over some region. That region can be a line, an area, or a volume, or something like that. You can imagine some piece of material and it is completely distributed with the charges, maybe some positive charges or some negative charges. All over this region or all over this volume there can be charges. So, actually in actual practice the charges may be distributed like this, but we can use this equation still, that is actual practice we have distribution of charges, but still we can apply the equation that we learned for discrete charges. Why? That is, you can consider this distribution as a point charge or as a discrete charge when you are looking very far away from this. For example, if this charge is at that much distance, if you are looking from this point, so from here if you are looking, you can consider this distribution of charge as a point charge. So, that is the importance of point charge. So, you can use this equation as well as the coming equation, but point charges are still important, that is you can calculate or you can assume a distribution as a point charge if you are looking far away from. So, but that is not the case always. We need to consider, so we may need to consider a bulk charge or a bulk distribution of charge from a nearer point. Now, the field point is very closer to the charge distribution. Now, how will we calculate the electric field, or how will we have to tackle with it? That is we are discussing. Okay. Now, what we are doing is that this is a bulk of charge, say some arbitrary shape material. Now, we want to calculate the electric field at this point. For this, what we are first do is that let me erase all this. Okay, that is still it is charged, that is it is positively charged, and now I consider a small piece of this material, maybe a cubic space, a very tiny material or part of this object. Now, let us assume that this small piece has a charge dq inside this. So, now from if you are looking to this charge dq from this point P, you can consider this piece as a point charge. Now, we can write the equation for that easily. That is, now what we are doing is that we are making this entire object as tiny pieces, and we calculate the field due to one of them. Okay. Let me write it as, the field will be very feeble. So, I write it as some dE. So, that dE is equal to 1 by 4 pi epsilon 0. Now, the charge is dq, that is dq divided by the separation vector. Now, the separation vector is some let me write it as, let this be the separation vector, and this separation vector is r, let it be some r. So, r square into r cap. Now, the equation for a very tiny part of this charge is okay. Now, what we have to do to get the total electric field due to all this, you have to consider another small piece. So, let us consider another small piece from here, another small piece from here, and calculate a dE1, dE2, dE3 and take the sum. That means, we are taking infinitesimally small pieces of charges and summing it up, and there is a mathematical technique to do that, that is called integration. Instead of summing it up individually, that is what we have done before, because we had discrete charges at that time we can count them, that is 1, 2, 3, that is why we use the symbol summation. Here we cannot sum it up because this is distributed continuously, you have to sum it also continuously. That continuous summation is called integration. So, to find the total field E, this becomes E is equal to 1 by 4 pi epsilon 0. This is a constant, that is why I took it outside. Now, I have to integrate it over dq divided by r square into r cap. Okay. Now, evaluate this integral to get the total electric field. This is how we could find the electric field due to a continuous charge distribution. Here you have to note one thing, here this r is not a constant. Okay. This r is variable. So, it has to be inside the integral. If it were a constant, I can took it outside, that is r square would have been here, and I can just integrate this dq, but not that, this r is varying. Why? That is, for this dq this is the r, but for this dq the r is another r. The r is varying when we are considering each piece of them. So, the sum is so that r should be inside the integral. Evaluate this integral to get the final answer. Okay. Now, that is it. Now, a little bit about the charge distributions. This is the whole point about the charge distribution. This can be used to find the electric field, and if you multiply the electric field with the test charge, then you can calculate the force also. Okay, that is all. Now, there are different kind of charge distributions. That means, the charge can be distributed over many dimensional things. That means, it can be distributed over a line or over an area or in a volume, and depending in that is, in these three kind of materials you can distribute charges over a line, over an area, over a volume. So, based on that we define 3 charge densities, which is very useful when dealing with objects of a line or a surface or something. So, at that times we can replace that, instead of dq we can replace it with the charge densities. I will show you that. Okay. That is, this is our equation, we have to replace this dq. So, now imagine you have a line something like this, and a charge is distributed over this. Okay. That means, some positive charge or a negative charge is distributed continuously over it. Okay. Now, I am considering a small piece of that, say this piece, the total length of the line be L, okay, and I am considering a very small, infinitesimally small part that has a length dl. So, I am considering a dl element. Element means a very small part of that, and let that have a charge dq. So, dq is the charge in dl length. Now, I can define a density here. That means, in dl length we have dq. That means, I define a density that is lambda, which is equal to dq by dl. That means, this is the charge. That means, in the numerator it is charge, and denominator it is length. That means, this is the charge per unit length of the wire, or we call it as, it is a density, that is something distributed over a line and we are dividing it with its geometry. So, we can call it as a density, and particularly it is called a linear charge density. So, this is linear charge density. So, when we are dealing with a line or an object whose length is very important, we can consider this lambda instead of anything else. So, it is, this becomes very simple. What is the advantage of this formulation? That is, in this equation what we need is dq. So, instead of this dq we can substitute dq is equal to lambda dl. Now, the integration becomes over the length. If lambda is constant, lambda may be a variable. If the lambda is a variable, then that has to also to be integrated. So, what is the advantage is that we can replace dq with this lambda dl. So, the integration might become simpler in that case. So, similarly, we have to define it for an area and also for a volume. Let us see that. Now, consider an area. So, some area, you have an area, it need not be flat, okay. It is a total area, and again as we mentioned before, now we are considering a small portion of it. that it is a total area. So, a small portion will be a smaller like a rectangle or a square in that. So, and we call it as dA for area, that means small piece of area, because the whole shape of this is 2 dimensional. So, we have to consider a 2 dimensional thing here, that is a very small or infinitesimal area or elemental area. And again we are saying that it consists of a charge dq. Now, that means dq amount of charge is distributed over an area dA. So, here also we define a charge density, that is dq divided by dA, that is here it is the charge and this is the area, that is this is charge per area, and we defined as sigma. Okay. Sigma is another term that is called the surface charge density, that is the charge density over a surface. Surface charge density. Obviously, the next would be volume charge density. So, here also we can replace this dq, that is to the equation we can put dq is equal to sigma dA. This comes to the integral. Okay. Now, the next is the volume charge density. Let us look for that. For that we have a bulk material. Say imagine this is not a plane, this is actually a 3 dimensional object, a bulk material, that means it has a 3 dimensional space, something like a sphere or some potato or something like that. Okay. So, it is a 3D thing. So, since it is a 3D thing, we have to consider an elemental volume, that means we here what is important is its volume. So, we have to consider a small volume in this, a very small volume or an elemental volume, and it has a volume d tau. Okay. Since we use tau this simple, because V is we are using here the V, usually we use V for volume, but in electrostatics we need this for potentials. So, we are reserving it for that, and now d tau is the volume, and again as that of same before, there is a charge dq and dq by d tau, and this is charge per volume, which is defined as a simple rho, and this is called volume charge density. Density, and here we can use dq is equal to rho d tau. So, when the densities are given, we can replace the integral, the dq term in the integral with these equations. That is, when we are dealing with volume, we can use rho d tau, and we are dealing with surface, we can replace it with the sigma dA and lambda dl for length. That is it. Okay. Now, we have all the tools, that is how to we know how to calculate the electric field for a discrete distribution, a continuous distribution, and now we are applying that to a particular problem. That we might think that the whole thing of electrostatics, actually almost all the things, basic things for electrostatics, the physical input of electrostatics is completed. That is, only what we do need is the that integral, that is equation to find electric field and the equation to find force, that is over. But there comes some problem, it is not complete yet. Why? Okay, we will discuss that with a problem. Now, we are applying what we have learned before. That is, what we have learned before was, we know that to find the electric field, now we have an equation, E is equal to 1 by 4 pi epsilon 0 integral dq divided by r square into r cap. Just evaluate this equation to get the value of any distribution, any kind of distribution, and we can replace with dq with some lambda dl sigma dA. That means, we can replace it with the charge densities. That is what we are talking. Now, here we are doing a problem using this equation. Okay. Now, let it be. Okay. So, we are considering a line, sorry, okay, we are considering a line of length L, okay, length 2L, let be 2L. So, the integration would be much easier, that is why we are using 2L. So, its total length is 2L and charge is distributed over this. So, this line consists of charge. So, this is a line. So, we can define a charge density, a line charge density for this, that is lambda. Let lambda be the line charge density for this line, okay, and its length is 2L. Now, we want to calculate the electric field due to this at a point exactly above the center of the line, okay, and let that distance be some z as we used before. Now, the important thing you have to notice that in the previous problem we have calculated some similar thing in the last class, that was actually you had a charge q here and another charge q here, only two discrete charges, but now the charges are distributed continuously over the surface, or sorry, over this line completely. That means, here you have positive, here you have positive, and almost everywhere over this line continuously everywhere you have this charge, okay. So, this is so in this case let us see how we will calculate the value, okay. So, for that we can use the above integral. So, what we are doing is that first of all, in such cases, that is when we want to find the electric field due to a continuous charge distribution, first of all we have to consider an elemental piece of this, a very small piece of this, then calculate the electric field due to that and then integrate, that is it, that simple it is. So, let me consider a piece here, okay, and before that let me set up a coordinate system as usual, okay. So, we have an x towards here and we have a nis, we have an z towards here. So, this is the x axis and this is the z axis. So, we have two axes here. Now, I am considering this. So, from the let this point be the origin. So, let me mark this point as the origin and this is the small element of this total length and let me call it as some d L. So, instead of d L I will put dx. Okay. Now, you can see the total length of this line is 2L. That means, if O is the center of the line, the origin is at the center, then up to this point will be plus L in the axis and this point will be minus L in the axis. That is, we set up the axis like that, we took this point as the origin, then this point will be minus L, this is plus L. So, minus L to plus L means total L length of 2L. Now, I consider a small dx here. Now, and the distance to this dx be this distance, that is origin to dx be x. Now, since it is symmetrical about this origin, symmetrical means there is equal amount plus L to the right as well as an equal amount minus L to the left. So, I can consider a similar piece here also. So, here also we can consider a similar piece, okay, of length again dx, which is at x. So, even if you consider another piece here, you can consider another dx here. So, symmetrically there will be another here. So, whenever you consider a dx here, simultaneously you can consider another dx here. It has an advantage when we are integrating. Okay. Now, we are calculating the field due to these two dx's. Now, you have two charges here. So, dx is a small piece. So, there will be a charge dq there and here also dq. So, what is this value of dq? Now, we know that lambda. So, lambda is the charge density, that is the charge per unit length. That means, in this lambda there will be a charge of, that is lambda times the length, or in the previous example we write the equation something like this, that is dq is equal to lambda into dl. Here the length is not dl, we took it as dx. So, we substitute that there. So, that is lambda d, sorry, lambda dx. So, lambda dx is the charge inside this dx and here also. And now, we have to calculate the force due the electric field due to these two individually. Let us calculate. So, first of all I am considering this dq. Okay. So, let me denote it as 1. Okay. So, the left to mark it just I put 1, and for that we have to do the regular thing, because we need r, that curly r, the separation vector, the source vector, the field vector. Okay. Now, so this is from here to here. Let me mark this. Okay. From here to here you have the source vector, because this small chunk of line it acts as a source. Okay. So, this is called the source vector, and this is the field point. This we want to calculate the field at this point and let it be p, and that is a field point. So, the vector to there is called the field vector. So, we got the field vector. It all starts from the origin. Actually, it goes exactly over this line. To distinguish, I just put it to the left of this line. Okay. So, this is the field line. Now, what is the separation vector? Separation vector starts from the source to the field. So, this is the separation vector. Let me name it. So, this is our r dash, and this is our r, and this is our curly r, the separation vector. Now, we have to calculate value of r. Now, what is r? R is equal to, we have already seen that, r minus r dash. So, what is the value of r? Okay. Now, the value of r means that is a vector from the origin to the field point, that is this vector, this perpendicular vector. That means its magnitude is z, that means p is at a distance z above the origin. So, the distance to there is z, and which is directed along the z direction. So, again its that vector is z cap. So, I can write it as z cap minus, the minus is from this equation. Now, there is an r dash. What is r dash vector? That vector is from origin to the left dq. Okay. That means it is along the minus x axis, because this is the positive x axis and this is the negative x axis. So, this is along the negative x axis. What is the magnitude of that vector? Yes, it is x distance from the origin. So, we can write it as x cap with a minus sign. Why the minus sign? Minus sign is because it is opposite to that of, its direction is opposite to that of the positive x. So, I can write it as minus x cap. So, now totally it becomes plus. So, we got r is equal to r minus r dash. Now, just write the equation. We know that E is equal to, let me write it as E1 is equal to 1 by 4 pi epsilon 0 dq. Okay. Now, we are calculating actually the force only due to this. So, let it be dq. What is the value of dq? Instead of dq, we can substitute lambda dx. So, that is lambda dx divided by, here we need r square, that is the distance square. So, distance square means that is, what is r square? R square is the square of its magnitude. What is the magnitude of this vector? Z square plus x square. It is z square plus x square. This is actually the square of the magnitude. The magnitude is only root of z square plus x square. We take the whole square to find r square. So, this is r square only. Okay. Z square plus r square, we can substitute that here. So, this is z square plus x square, and into we have to substitute r cap here. What we do for r cap? We know that r cap is vector r divided by r. So, vector r is z cap plus x cap divided by r square is z square, r is, so what is r? We know the definition of the unit vector, r is equal to vector r divided by magnitude r. what is the magnitude are z square plus x square the whole raised to 1 by 2. So, this has to be come here, this has to come here. So, that is z cap plus x cap divided by z square plus x square the whole raised to 1 by 2, z square plus x square the whole raised to 1 by 2. Okay. Now, let us see, we can combine it together to get 1 by 4 pi epsilon 0 lambda dx divided by, this becomes z square plus the whole raised to 1, this is 1 by 2, that is totally z square plus x square the whole raised to 3 by 2 into z cap plus x cap. So, we got one of the field due to that small dq. Now, we have to find another one, that is E2 due to the right small dq. Okay. So, for that let us go back to our image. Here, this is our image. I am not completely doing it, that it is a similar thing, because you can see here we have a dq here. So, since we have a dq here, you can draw a position vector to here, and this is the old position vector, that is the field vector, it is the same, but the source vector is different, it is along the positive direction, and you have the separation vector here. So, what is the separation vector? R minus R dash. R is z cap minus, now the x is positive, this is along the positive direction. So, x cap. So, this will be the, that is the only difference that makes there. So, we can formulate the equation for E2 there. Okay. Okay. Now, we got E1, and from the figure we got for the second case. So, for the second case, that is for the right charge, the charge at the right side of that origin, we have to write the equation. So, for that we know R, the vector R, that is for that we can write R2, which is equal to z cap minus x cap, that we got from the figure. Now, let us write the equation, that is E2 is equal to 1 by 4 pi epsilon 0, again the lambda dx, there is no difference in that, and the magnitude of this equation, this is z and x, that is z square plus x square, z square plus x square into R2 cap. What is R2 cap? Let us find it out. R2 cap is equal to vector R2, that is z cap minus x cap divided by its magnitude, that is z square plus x square the whole raised to 1 by 2. Let us substitute that to here, we will substitute it here, and we get, let us see, okay, let us substitute it here, we get z cap minus x cap divided by z square plus x square the whole raised to 1 by 2. So, now the equation becomes E2 is equal to 1 by 4 pi epsilon 0 lambda dx divided by z square plus x square the whole raised to 3 by 2 into 3 by 2 means this is 1, this is 1 by 2, the sum will be 3 by 2, that is into z cap minus x cap. We got it. Now, we got two equation, one is due to the charge, one is the electric field, that E1 is the electric field due to the charge at the left side, and we will just draw roughly that figure here, that is we have something like this, this is minus L, this is plus L, and this is our dq and dq. Now, this is B. Now, we got an equation, that is E1, we calculated E1 for, so this is our E1, the expression for E1 is this. So, E1 is the electric field due to this dq, and E2 we calculated, that is the electric field due to this dq. Now, we got 2, only 2, very tiny part of 2, and we can sum it up. So, we will sum it up, that is E1 plus E2. Now, when we are adding E1 plus E2, you can see here there is 1 by 4 pi epsilon 0 lambda dx z square plus x square the whole raised to 3 by 2. Now, all these are same here, and z cap also same, but plus x cap and minus x cap, they will cancel out. So, what we got, you have to take the sum of these two only, that becomes they are same. So, 2 times. So, I can write E is equal to, so I can write E is equal to 1 by 4 pi epsilon 0 2 into that 2 because here an z cap, here also an z cap. So, they sum it up to 2, that is 2 lambda dx divided by z square plus x square the whole raised to 3 by 2 into z cap. Now, we got an equation for E. This is not the final answer. Why? This is only the field due to this dq and dq. So, it will be a very feeble electric field. Let me write it as some dE. Now, to find the total electric field, we have to integrate, then only we can take the next piece, we have to make it into very tiny pieces, and we have to consider it all. So, for that we do integration, and that integration is, we have to integrate this expression. So, what is this expression? So, the final electric field, the total electric field is equal to 1 by 4 pi epsilon 0 integral 2 lambda dx by z square plus x square the whole raised to 3 by 2 into z cap. You have to integrate this to find the answer, and what should be its limit? Is it from minus L to plus L? No. Why? We have already considered these two together. So, you have to just take from 0 to L, that means from origin to L is enough. That is, we are considering only when we are integrating from 0 to L, you are only considering one of this element. No. Why? Because when we are considering one of this element, simultaneously you are considering another one. That is done by this two. That is why we are done. We have considered these two together. Okay. So, automatically you have to integrate only from 0 to L. This integral will automatically run from minus L to plus L due to the presence of this 2. So, we can write it as minus L, sorry, not minus L, okay, that is 0 to L. Just integrate this to get the final answer. Okay. Now, we will discuss that integration in the next class, and this is enough, I think, for this class, and thank you.